Starting the recording right now for the lecture on the hash functions. Last time we stopped discussing the collision resistance and the birthday paradox. And the birthday paradox basically it explains, as was illustrated in the class, that it's easier to find two inputs. um, Okay, let me just try to put this in presentation mode. It's easier to find that to find two inputs that produce the same output in a hash function. And basically, it is illustrated with this very famous case here. Despite the fact that I have 365 days, but it takes 23 people, 23 trials to find two people with the same birthday at a probability of 50%. There is, as we stated in the class, there is really a good mathematical derivation for this one, but we picked up the formula from the math books, and we use it here. So if you have impossible values, in this case, m, the 365 days, and we would want to try a k trials here. We want to find out how many people we need to pick so that I will have a collision, meaning I will have two people with the same birthday and with a probability of p. Math tells us that k is equal the square root of -2 multiplied by m multiplied by ln, the logarithm of 1 minus p. And if we take the square root of m outside, all right, then we are left here with square root of, now we merge the -2 with this one here, square root of ln 1 minus 1 over 1 minus p square. And we can solve the formula for the birthday example here, and we get 22.5. That's 23 persons. We cannot have 22.5 persons. We have 23 persons. Now, the most important thing here is to realize that if we stick with the 50%, then this square root comes about 1.1, 1.2. Okay, so if we have a 128-bit hash output, so the number of the number of possible values is 2 to the 128. And this, and we're looking for a collision of 50%. We know from this above simplification that this whole thing will simplify to 1.1. We're going to have to square root the 2 to 128. We get 2 to the 26.4, which means despite the fact that I have a hash function with a digest output of 128-bit, I will have enough. My trial complexities is 2 to the power 64, which is almost with a probability of collision of 50%, which I lost half of my bits. So, for instance, if somebody shows up with a hash function with 64-bit, right? In a small laptop, you can hit all the 32 values with the 2 to the 32 with the probability of 50%. So the birthday paradox here really, it is really easier to find two inputs to produce the same output. In particular, if you are looking for a collision resistance with a probability or a chance of 50%. That's where we stopped last time. Okay, so in general, hash functions, um, if you look at them, you have the data, the message right here, consisting of L blocks, right? Every block has B bits. For example, in the SHA-2, this 512, this can be in one of the SHAs with algorithms that we talk about, 1024 bits. And then this block will goes to this hash function, which receive two inputs, one block from the message with the P bits, and in the first stage initialization vector with n, typically n less than b. So n can be, for example, if b 1024, n will be, for example, 512 bits. We will go through this hash function and it produce the chain variable v1. So this is vcv0. At the first stage, we'll have an initialization vector. We'll take the b bits from the block y0 and the n bits from the initialization vector, crunch the number here in this hash function, and produce n bits for CV1. Do the same thing. We go to the next block, which has b bits, for example, 1024 bits, with the output of the previous stage, 512 bits, crunch them in this hash function, and so on and so forth until I process all the blocks. The message size here is B, right, times L, because here I have L blocks, right? And F, it takes here two inputs, B bits and N bits, and produces N bits. So this is my hash function. This is typically the general structure of a hash function, at least for the SHA-1 and SHA-2 and SHA-3. Okay, how to implement hash functions? In the past, people used the symmetric algorithm to produce hash function. A number of proposals have been made for hash function based on using cipher blockchain, a blockchaining mode, a technique, but without the secret key. If you recall, we covered this cipher blockchaining in an earlier lecture. Okay, we do this without a key. Probably you might need an initialization or a secret, let's say, vector here that can replace the key. But at any rate, we don't have a key. Typically, key has required number of bits and it has to be shared. So you can see here that by going through this chain, the last CN here, which is supposed to be one of the ciphers for cipher blocks, will be my hash output or a hash digest. So one of the proposals was that of Rabin, divide a message M into fixed size blocks, M1, M2, Mn, and then use symmetric encryption. And the symmetric encryption we have for the it goes through different layers, hash 0, hash 1, hash 2, hash 3, hash 4, as it processes these blocks. Initially we'll have to have an initial value, and then in every stage we encrypt the previous output, right, with the block of this stage. Now notice that these are the blocks. And at the last stage, we generate the last stage, which generates HN, becomes my digest here. So basically, instead of going here to an XOR, okay, maybe the C1 will replace the key here, and C2 will replace the key, etc., etc. Okay. All right. Similar to CBC technique, but yeah, what we have explained, we stress on there is no secret key. We don't use a key here because one of the principal things about hash function, it does not require a key. As with any hash code, this scheme subject to birthday attack. Okay, so if you have a hash output of 64-bit, right? In the case of a DES algorithm, well, we just stated that the birthday attack, you need only 2 to the power 32-bit trials, 1.17 times 2 to the power 32 trials to get a collision with a probability of a 50% collision. So that's not secure. That's absolutely not secure. Okay. So meet in the middle attack also, these type of early hash functions are vulnerable to. So in summary, while they look attractive, you can chain them, easy to be implemented. You can use symmetric algorithm. They are not safe and should not be used. Then came the era of secure hash algorithms, and for short we call them SHA algorithms. And those SHA algorithms have gone through really multiple stages. The very early SHA, that was SHA-0, it was released and withdrawn very quickly because of major flaw in the algorithm. So people sometimes don't even mention that. The first SHA was SHA-1, and then second generation SHA-2, and third generation SHA-3. Keep in mind that for every algorithm, we can talk about characteristics or parameters of that algorithm. One of them is the maximum message size, for instance, the block size, okay, the word size. The output is very important because this is what determines security along with the complexity of the hash function. Internal state, okay, rounds, and when it was published. So the SHA-1, we know it is one output of 160, okay, very early stage of the algorithms. This is the maximum message size, okay. Then came on the SHA-2 with two major flavors, 256 output and 512 output, okay. And the main thing is that you can see that this increment in the number of the output digest, the output digest size increased from 160 to 256 and 512. Excuse me. That was released in early millennium. And then we have the SHA-3, okay, the SHA-3. Let's see. Where was my pointer? Okay, here's the SHA-3 with multiple flavors. You have the unlimited, you have the unlimited message size, and then we have the 250, 224, 256, 384, 512, etc. And there is one last one was suggested, which is the this is the SHA KE. I don't know how the shake, probably 128. And this all came from the algorithm KCAC, which was the winner of the uh, algorithms, the class of algorithms, when proposals were submitted to upgrade from SHA-2. Okay, so typically people refer to this green one as SHA-1 and SHA-2, this one here, and SHA-3. We will study in the next slide the SHA-2. Remember, there are two flavors. We'll look at the output with the 512 bits, and the block size that we consumes is 1024, and the maximum message size is 128. So let's focus on that in the next slides. This is the message size again. Okay, it should be multiple of 1024 bits. You can have one block, two blocks, etc. However, you should not exceed the number of bits. It should not exceed 2 to the 128 bits. Now, there is one last block here that typically is added. It includes padding of 1 and bunch of zeros, and then at the end here we have the message size. Okay, L indicates that there are 128 bits. If you look at this block here, okay, we see that it consists of these blocks, all right, and there are n of them, and every block is 1024 bits. If we examine how many words we have, assuming my word is 64-bit, then we have 16 words in every block. And the output of this algorithm is 512, which means it is 8 words times 64, assuming that the words is 64. So you have here multiple blocks, okay? So we will process those block by block. We take the first block, 1024 bits, we send it off to the hash function here, which we'll explain in details. And from the previous stage, and in this case, since we are in the first stage, we'll use an initialization vector. The H function from this previous stage will go to the hash function and will be used in the addition here, okay, for the output of this hash function. And then this produces the H for the next stage. And you can see that those H's they have the size of the output of the algorithm, which is 512. Okay. Now, in every hash function here, we have 80 rounds here. We have 80 rounds. In fact, if you look at the previous table here, we mentioned how many rounds we go. So if we look at this algorithm here, which we are focusing on, right, there for every block to be processed, we go through 80 rounds. Now, we move on to the next block. We do the same thing. We send it off to the hash function. We spend 80 rounds. We use the H from the previous stage to crunch the number in the hash function, and to do an add here, okay, and produce H2, and etc., etc., etc. After I process the last block here, okay, and we can after I process the last block, we can produce now the output, or we can claim that we have the output of the hash function. Now, in terms of the last block, there might be here a few bits extra, so we pad them all the way 10000 all the way to the last 128 bits. We leave those 128 bits because they will tell me the size in bits of the message. Okay, not in number of blocks, in number of bits. All right, so this is the hash algorithm. It's a lot to unpack here, but we'll go through the whole thing and just throw this and then we will SHA 512. By the way, it's SHA 2 512 refers to the size of the output of the hash function. Now we can see here that clearly we are zooming in more into the algorithm, okay, and you can see here the extra bits here. We'll talk about the appending these bits. You can see here or padding the bits. You can see here is the message here that we have a few bits here left over. They cannot make a full block. So what we do, we append those bits, but we leave here 128 bits so that I can state the length of the message. Okay, so we can see this here, this section here is part of the message. This here padding, and this is here 128 bits indicates for me how many, the size of the message. Okay. Right. So you can see the padding here is 1 followed by zeros. Okay. So even if the padding is always added, even if the message is already in the desired length. So for instance, if you have your message here stops here, you have to do padding for the last block. So this block is added anyways. Okay. So with okay. So this block of 128 bits indicates I'm sorry, this chunk of 128 bits indicates the length of the message, as we indicated earlier. Before we start the algorithm, we have this 512 buffer that will continue with me from a stage to a stage, and this 512 buffer would like to split it into 8 registers, and every register of them is 64-bit, and we will call them A, B, C, D, F, G, H, and if you multiply 8 times 64, you get 512. So this buffer is going to continue with me along the algorithm. These are the initial values, right, that we will initialize them when we start the algorithm. Okay. Sorry. Now, so here is what happens in every block. When this is here one of the blocks, okay, and it goes through a message schedule, and this message schedule will compute W0 all the way to W79. So there are 80 of these W's. Then we're going to have this hash value or intermediate hash, which was computed from the previous stage. And we say this is 512. And then we will have eight of these registers, right? And those registers, every one of them is 64. And they're going to go to this function here. And they will complete 80 rounds. In every round, we will get one of those W's, and we will get one of those K's. These are pre-computed constants. We have K0, K1, K2. So for round 0, we will get W0 from here, from the message schedule, and we will have a constant K0. Both are 64-bit. They will receive these 8 also with the 8 registers here of 64, and we're going to crunch the numbers here, right? And then we will produce 8 values, which will be added to the previous H here, right? And produce for us 512 bits. And this is going to be my HI, which is the output of this stage. But remember, we're going to do this addition, right? after we finish 80 rounds here. Okay, we have to go through here in 80 rounds. Then we go through this add, and this produces HI, and this becomes the output of this stage. And then we go to the next block, which is the block after this MI. Every block of those is 1024 bits. Okay, so to process this block and produce HI here, I have to do and go through all of this in front of me. Okay, now, so basically a different view here. We get this HI here. We split it into those 8 registers, every register 64. We process round 0 gets K0 and W0. Exactly what we mentioned before, but in a different view here. Round T, we get WT, KT with those registers A, B, C, D, E, F, G, H. Process things and etc. all the way to round 79. And then we add these registers A, B, C, D with the earlier register values here, addition. Okay, every 64-bit is added separately, and then we get the value of these 8 registers A, B, C, D, E, F, G, H. 8 times 64, that's 512. So HI here is 512. I started with HI minus 1, which means the output of the previous stage, and I produce the output for processing MI. HI for processing MI. Okay? So obviously you can see round 0, round all the way to round 79. Okay, then we get into the question is what happens inside here, inside the round? Well, clearly this is where the magic and the secret sauce. These are my registers A, B, C, D, E, F, G, H. Every one of those is 64-bit. 8 registers, 64-bit each. That is 512 bits here. And I'm going to go through math here and produce 512-bit here. So this is exactly what happens in each of these rounds. In each of these rounds. And this one, and this one, and this one. Okay, so we have a function here, a majority function, and all these summation functions. I'm gonna explain those in my next lecture, and we'll stop at this point because this is, I hate to interrupt my explanation for this one because it will take me more than 15 minutes to explain. So I would rather have it in a more continuous session and setup, and we'll leave it for next class. Thank you very much, and this is the end of the recording.